Haşim Bey, şu an canlı yayın başladı.
Okay, hello everyone. Welcome to our first webinar as our 50 years anniversary in ISCC and also part of our ISCC 2022 events, which is International Symposium on Contamination Control. As Cleanroom Technology Society of Turkey, we will be the host country of this event, and we will be in Antalya this year in October. I'm going to share more details about this event later on. Let's move on with the presentation. I just wait a couple of minutes because the live stream, when it goes on, everyone has a couple of minutes to log into the system so that we will be waiting for them to join us. And let's move on. Okay, my name is Haşim Solmaz, and I'm a general manager of Lighthouse Worldwide Solutions and working as responsible for the EMEA operations. I have different hats in different organizations internationally, but today I'm here with you as part of Cleanroom Technology Society of Turkey, ISCC and ISCC 2022 organization. Today we are going to talk about the contamination control, and we will be touching basics of air filtration systems. There is a general expectation from the filtration technologies that they will be keeping our clean rooms and clean environments safe and clean. Apart from this, there are international regulations and norms where we are applying for the filter technologies from the manufacturer side, also the same technologies that we are implementing in the on-site filter installation. And after that, we will be talking about the cleanroom monitoring, environmental monitoring systems. And I'm going to give you an example for the non-viable systems. And these non-viable systems will allow us to see how we will be preparing our risk-based approach to the system. And after that, I will be giving you an application examples with a risk-based approach. Let's start with contamination control and air filtration systems in a clean room. We all know that the HEPA filters, or the higher quality filters, the classification filters, are the main body of our contamination control. So all air handling units and the systems that we are welcoming air into our clean room has to go through these filtration technologies. The theory behind is to have these fiberglass filter media along with the technology that allows us to pleat them and put it into the frame. And in general, this is how we are having these high technology filtering systems. And also for the raw filtration, where we are using for the return air, or just to take the air into our air handling units from direct atmospheric conditions, we have these non-woven filter media, where we are placing this as a raw filtration technology. For the filtration basics, based on the efficiency, when we're talking about the efficiency, we're just making a comparison between our inlet air, which is called an upstream, and the outlet air, which is our downstream. So if you divide the downstream to the upstream as a percentage, you'll be getting the efficiency of each filter. So based on the regulations, there are EPA, which is efficient particulate air filters, or HEPA, which is high efficiency particulate air filters, or ULPA air filters, which is ultra low penetration, which has a lot of nines after the first digit and allow you to keep as much particles away from your clean room environment. If you take a closer look to the EPA filters, you'll be seeing this mesh system, which you have all the fiber media into the surface. But if you take a look at the HEPA filters, this mesh mechanism is getting narrower and not allowing more particles to penetrate. But if you take a look at the ULPA filter, as an example on the right side, you'll be seeing your hair on the left side. It's just the blood cell as a size comparison. So these ULPA filters has a very small and very dense conditions where not allowing your particles to get into your clean room. When we are talking about the filtration basics and its theory, we have to know how we are collecting all these particles. So I have a small video for each mechanism. While I'm explaining it to you, I'm going to share this video with you too. Sieving effect, most of us are expecting this is the main mechanism of filtration, but in fact, straining only accounts for 1% of the particles captured by the filter. And this larger mechanism, larger particles, are stripped by the filter media itself. And this strip mechanism is just catching the particles which are larger than the expected sizes. The second one is inertial separation. The second one is the inertial separation concept. This inertial separation concept has the largest particles that are having their own momentum, which makes it more difficult for them to follow the airstream around the fiber. Here is a good way to think about how impaction works. Both water and air are the fluids, so they move it in much the same way. Think of the water in the stream. If the leaves are in the current approaching a rock in the stream, where the move is around the rock. So if the leaves are catched by the system itself, then this mechanism is exactly the same way, collects all the particles from the surface. And the next one, interception concept. This interception concept is where we are collecting 30 to 40% of all particles from the mechanism itself. As you can see in the video, small particles flow the airflow around the fiber and captured if they came close enough to the fiber. The last method that I'm going to discuss here is the diffusion, and also here I will be showing you the video again. Lengthwise direction of the media filters can be found only in the case of very small particles, such as viruses. The name comes from how small particles travel in the air. This is what we call the diffusion concept. And this diffusion concept is one of the highest efficient media that we are, as I'm showing you here, that's one of the largest mechanism that we are using together with electrostatic attraction force. These electrostatic attraction concept, I'll be waiting for the video. This electrostatic attraction concept occurs when particles are attracted to the fibers by electrostatic adhesion. All particles and fibers has a small positive or a negative charge. Therefore, they have an inherent attraction to each other and end up being a part of our structure. So if you take a look at this graph here, which is known as most penetrated particle size for HEPA filters, or the other filter media as well, but here my example is for HEPA. As you can see on the left side, diffusion and electrostatic attraction is the highest impact on all particles. And then the straining and impingement, which is impaction and interception methods, are on the right side. Particles smaller than 0.4, 0.3 micron can easily be attracted by this diffusion and electrostatic force, while these forces are going low of impact after 0.5 micron. And on the right side, the straining and impingement methods are going higher after 0.4, 0.5 micron, depending on the particle sizes. So the sieving effect also supporting us on the right side. So this most penetrating particle size is our lowest possible attraction area. This doesn't mean, for example, in this example, if we are considering our MPPS is 0.4 micron, this is the lowest efficient location for our filter, HEPA filter. And this doesn't mean that we're not able to capture smaller than 0.4 micron if MPPS value is based on 0.4 micron. In fact, we will have a higher efficiency on the both sides of our curve. Reason I'm explaining, when we are having these coronavirus discussions as a virus, we all know that this is smaller than 0.1 micron. However, each HEPA filter can easily attract almost 100% of particles smaller than 0.1 micron, thanks to this diffusion and electrostatic forces. Our weakest point is our MPPS value, which is, for example, 0.54 micron here. And types of filters and their efficiency based on these MPPS value according to EN 1822 is given in this list. And the class goes from A10, which is the lowest efficiency, 15%, and penetration is equal to 15%, gives us an efficiency of 85. As you can see in ULPA U17, it goes all the way to 99.999995%, which is a very high efficient HEPA filters. And EN 1822, it's dealing with the performance of test of efficient particulate air filters, high efficiency particulate air filters, and ultra low penetration air filters at the manufacturer's side. Important note here is this sentence, at the manufacturer's side, because we're not implementing this into the field HEPA filters or testing the in situ installed HEPA filters in the final locations. In fact, this is the certification where our filter manufacturers are doing some certain tests with a specially designed equipment. These equipments has a particle counters in it, and these particle counters are counting particles in a synchronous way. And as you can see in the map, in the graph here, every single location of a HEPA filter gives us an output, and this output allows us to get the efficiency of our filter from every single point, different than what we are doing in field. So the final report is something like this, as you can see in the picture. Most of HEPA filters has this, and this shows us we have hash 14 efficiency according to EN 1722 for this HEPA filter. And the efficiency, as you see here, the MPPS value was 0.18 micrometer, and the efficiency is 99.999719. So it gives us hash 14 as a scale. Of course, EN is an European norm, but for internationally recognized, we always have these ISO norms as well. So there is ISO 29463-4, published in 2017, which is test methods for determining leakage of filter elements with a scan method. This is also for the manufacturers. In fact, this doesn't replace the EN 1822 standard. This European norm, will remain the same. As you see here, there's a comparison between these two, EN norm versus the ISO norm. It's quite similar, just converting EN norm to the ISO standard so that it will be recognized for the international, for the other countries outside of Europe. Yayın 16890, published in 2016. This is air filter for general filtration, part 1, technical specifications, requirements and classification systems based upon particulate matter efficiency. And this superseded EN 79, which was published in 2012 and replaced with these new ISO standards. In the US, we have these ASHRAE standard, which is 52.2. It's a MERV rating. It's quite similar with the EN, but just specifically designed for the US manufacturers for the domestic market. And there is very important recommended practice series from the IEST, Institute of Environmental Science and Technology from United States. There are a couple of important recommended practices, which is also the part of ISO preparation, especially for the installed filter leakage test. But as you can see here, the first recommended practice was about the HEPA and ULPA filters and how it describes the both methods. And testing ULPA filters giving as 7.3, and we have these 21.4, which is HEPA and ULPA media filter testing for the installed filters. And there is also the leakage test, where we are using the test, which is described in 34.4, where we are using the leakage test after installing these filters into the clean room. ISO 14644-3, which is a test methods for clean rooms and associated environments. These tests are performed to confirm that the final high-efficiency air filter system is properly installed by verifying the absence of bypass leakage in the air filter installation and that the filters are free of defects, small holes, or other damage in the filter medium, frame, or seal, and the leaks in the filter bank framework. So this is completely final filter testing in a clean room, and we are not checking the efficiency of filter itself. We are just making sure that the filter has no holes, no damage in the filter medium, frame, or the filter bank. These tests are not used to determine the efficiency of the filter medium. This is clearly described in ISO 14644-3 as well. That's why we don't have to worry about whether we are having the first installed filter in H14 or H13. In fact, this has to be done at the factory. We're just making sure that there's no leakage on our filter. As a summary, efficiency testing versus installed filter integrity testing. The test location has to be for the efficiency testing. This has to be the factory, the manufacturer, or the laboratory, third-party laboratory for certification. But for the installed filter, it has to be on-site within your clean room or the field test, but the filter should be installed first. And the aim of the filter testing for efficiency is to verify that the material and or the finished product meets the efficiency criteria. However, for installed filter, our aim is to verify that the filter integrity is maintained. In terms of particle generation, we have to focus on our MPPS particle size so that we will be able to generate more particles with this way. But for the installed filter integrity testing, the standard ISO 14644-3 defines 0.2 to 0.7 micron with a geometric standard deviation up to 1.7, which has to be calibrated for our aerosol generators, if even we are using photometers or the particle counters for testing, these aerosol generators has to work between 0.3 to 0.7 micrometer particle sizes. And the leakage type and the reason for the efficiency due to the poor media, maybe, the quality of the production, maybe, but it's all related to the textile or the production. But leakage reason could be for installed filter testing, could be physical damages, installation problems, or mechanical damage during logistics or the storage deficits. So we want to make sure that the filter already certified at the manufacturer's site during transportation and installation. We take care of it in a very good manner, installed it perfectly, then we are making a final test as an installed filter integrity testing. So if we move into the cleanroom monitoring part, we'll be starting with current GMP, which was published in 2008 and still in place. We all know that 2020 we find a draft, which I will be discussed later on during this presentation, but still we are implementing a GMP Annex 1 2008 version. This version, clause 9, clause 8 to 16, talks about the clean room and clean air device monitoring. So I'm going to go each and every clause so that we will be seeing the summary of each section and we will be adding our comments on top of it. First of all, clause 8 says clean rooms should be routinely monitored in operation and the monitoring location based on a formal risk study and the results obtained during the classification. So while you are doing classification in your clean room, you have to make sure that you are also preparing an output for your monitoring study based on your risk assessment. Clause number 9 is talking about, for grade A zones, the particle monitoring, the full duration of critical processing, including assembly, and except where justified by contaminants in the process that will damage the particle counter or present a hazard, example, live organisms or radioactivity hazards. In such cases, monitoring during routine equipment setup operations should be undertaken prior to export to the risk. So we will be monitoring the entire area. These monitoring may not be possible due to the product itself. For example, if you are manufacturing the dust-based powder filling line, for example, you can stop your particle counter during these powder fill. But before this, you have to monitor, and after this process, you have to monitor, and you will be make sure that within these two phases, you will be in the safe side. So there is no impact on your HVAC system over your unidirectional flow in grade A zones. And if you continue with the clause 9, this monitoring during simulated operations should also be performed, not limited with our media field studies, but also if you have any simulations that you are encounter for your production, then these monitoring systems should be up and running so that the output will be the output will give you the right impact on your final decision. The grade A zone should be monitored at a frequency and with suitable sample size that all interventions, transient events, and any alarm, any system deterioration would be captured, and the system should trigger your alarm if you exceed your alarm limits. So only monitoring is not enough here. You should have a system along with the particle counters. There should be a system for alarming so that you will be warning your operators. Reason I'm saying collecting data is important for sure, but at the end of the process, if you have a lot of alarm conditions right after your production, if you don't know, if your operator doesn't know anything about these alarms, then all the production might be a waste of time. That's why giving an alarm, triggering an alarm is important with these automatic systems. And also, this doesn't mean 724 up and running particle monitoring system. When we say it online, most of the people think that you have to monitor 7 days, 24 hours. That's not true. Before your production, you should take at least half an hour of the preparation time, and during entire production, and right after production until the cleaning cycle, you have to monitor it. This is what we call online. So in some cases, even the weekends, while you're not working in the area, your system is running. So generating, sometimes the system counts some particles, you don't know the reason, and you have nothing to do with this information. That's why you have to focus on the production time and consider it as an online monitoring. This is accepted that it may not always be possible to demonstrate low level of 5 micron equal and larger particles at the point of fill when the filling is in progress due to the generation of particles or droplets from the product itself. Let's not limit this with the production location. In some cases, due to nature of production, these particles can have a peak count where you'll have these peaks and monitor them. If it's a one-time issue, then you'll be safe. But if the peak is continue with a certain period of time, or the peak is related to any actions that you are taking on your production, for example, while you are loading stoppers into the stopper bowl, you start getting the peaks on your filling point, then this is indicating the poor design. So it has to be investigated and has to be fixed. But if it's just a one-time peak, if it's not returning back, if you're not seeing the same peak in a same condition, then it will be fine. So clause number 10, it's recommended that a similar system to be used for grade B zones, although the sample frequency may be decreased. Sample frequency, the number of locations can be summarized, or the duration of sample progress. Both is fine. We don't need to place a lot of particle counters around this grade A zones as a grade B, but still we have to monitor, especially nearby our operators and the return air, based on our risk assessment. The grade B zone should be monitored at such a frequency and with a suitable sample size that the changes in the level of contamination and any system deterioration would be captured and alarm triggered if alarm limits are exceeded. It's exactly the same definition with clause 8 for grade A. And clause 11 is talking about the independent particle counters will be needed for the system. And you have to select an appropriate particle size. For GMP, this is 0.5 and 5 micron, but you can consider adding 0.5, 1 and 5 micron. But personal comment here, even GMP revision tells you to have 5 micron not to be monitored. Even in the revision version, we will come later on, they still kept this 5 microns. Even if they remove, I recommend you to not to remove it, because this is an early indication of your HVAC system failure, having these 5 microns. That's why it's quite critical. And if you are using remote sample systems, the sample tubing, the length of this tube, and the radius of any bends has to be considered as a risk point. Reason I'm saying, you may start losing particles on your tubing, and also the radius of your bending. If it is small, then you will start again losing your particles from your sampling into your sampling system. So make sure that you have enough engineering study behind and keep it as short as possible. The selection of the monitoring system should take account of any risk presented by the material used in the manufacturing operation, for example, those involving live organisms or radiopharmaceuticals. Clause 13. The sample sizes taken for monitoring purposes using automated system will usually be a function of sampling rate of the system used. It is not necessary for the sample volume to be the same as the used for formal classification of clean rooms. That's quite critical, because you know the table in Annex 1 2008 version given as a meter cube of data. So most of the people consider collecting these 1 cubic meter of air with 1 CFM particle counters, which takes 36 minutes. So during this 36 minutes, they're waiting until counting this data, and start initiating their alarm systems, or they are using moving window of these 36 minutes. That's not a good practice. According to here, clause 12, the sampling rate should be the function of the sample system that you are using. For example, if you are sampling 28.3 liters per minute, so divide all the numbers into, from the table, divide all the numbers into these and make sure that every minute you are giving a feedback. For 5 micron, it's not easy to give these feedback because you cannot divide 20 to 36 for this example, but don't worry about it because your aim during production regarding 5 micron has to be 0. So if you're getting 1, you should warn yourself. If you start getting 2, then this should be an action. This should be the point where you need to take immediate action for your system because we don't want to see these 5 microns. Even for classification, there is a limit, but still we have to make sure that we are not having 5 microns, which is a potential threat from your HVAC system. Clause 13, grade A and B zones, the monitoring of 0.5 micron particle concentration could take some particular significance as its importance diagnostics tool for early detection of failure, especially from your HVAC system, like we said. But the occasional indication of 5 micron may be a false count due to the electronic noise, stray light, or coincidence on your particle counter. So you'll be safe. Don't worry about this. If it's just one-time issue, then no problem. However, consecutive or regular counting of low levels is an indicator of a possible contamination event and should be investigated. Such events may indicate early failure of the HVAC system, filling equipment failure, or may also be diagnostic of poor practices during machine setup and routine operation. So this has to be investigated. Clause number 14 is giving us this, and the period as a guidance value giving us as a 15 to 20 minutes, but we can expand it all the way to 30 minutes just to be on the safe side. And as you can see here, the at rest value for 0.5 and 5 micron, as well as in operation value for 0.5 and 5 micron on the table. The monitoring of grade C and D areas is in operation should be performed in accordance with the principles or risk study. So if you have any if you have a risk-based study on your system and find out that the grade C or even grade D has a special application from your production, then you can consider having a monitoring system. In fact, most of the time, since the risk-based approach is mostly focused on the grade A and B areas, for example, the aseptic processing or aseptic manipulation, they're all going under these grade A conditions. That's why most of the risks are moving to A and B areas. The requirement of alarm and action limits will depend on the nature of operations carried out, but the recommended cleanup period should be attained. Clause 16, other characteristics such as temperature and relative humidity depending on the product and nature of operations carried out. The parameter should not interfere with the defined cleanliness standard. If you take a look at the GMP Annex 1 2020 draft, we will be seeing that there is a 2 parts which is described here in general, 9.1 up to 9.3. Environmental monitor as a non-viable particles, environmental and personal monitor as a viable particles, and aseptic process simulation, also known as a media field, as a different chapter. So these are all giving us a process monitoring, especially viable and non-viable monitoring. 9.1 to 9.3 telling us that the contamination control strategy is an important part to understand overall risk from our monitoring system. So this is the most important part and the value-added part of the revision in 2020. Still draft, still not published, I have to say, but they're working on it and will be alive. And this contamination control strategy definitely will be the part of this new Annex 1. and designed to minimize the risk of microbiological and particulate contamination. When considered together, their reliability is dependent on the design, validation, and operation of the system that they are monitoring. The information from these systems should be used for routine batch certification and for periodic assessment during process review and investigation. So for environmental monitoring, we already know that this environmental monitoring, whatever we see in 2008 version, still exists. That's why it says as a value-added part, we're start talking about the risk assessment. This says you should have a detailed knowledge of the process and the process input and final product. You should know your facility very well, specific process applications on your own production, the operations involved, the historical monitoring data as a trend, and qualification data where you are using as a clean room classification. So it's not possible to collect all this information from the quality department or from engineering. So different departments, the stakeholders should come together and discuss about these risk assessment. So risk assessment has to be done with engineering, with quality department, with production, with qualification, so that everyone will know the part of their job. Everyone will know what will be the risk and how they will be monitoring it in a long run. The routine monitoring of clean rooms, clean air equipments, and personnel should be performed in operation throughout all critical stages, including equipment setup. So it's not limited with the production itself. It should start with the equipment setup all the way till the end of our process. Appropriate alert levels and action limits should be set for the results of viable and non-viable particle monitoring. This is still exists in 2020 draft. Trending become very important part of our structure because we want to know where we are moving forward. Trends can include, but are not limited to, increasing number of action limits or level breaches, alert level breaches, consecutive breaches of alert levels. Maybe you are getting one peak, but if these one peaks getting, let's say last month it was every 10 minutes, 15 minutes, but we are start getting every 5 minutes, then something going wrong. So that's why the trending of your alert limits is important. Regular but isolated breaches of action limits that may have a common cause. For example, single exertions that always follow plant preventative maintenance, changing HEPA filters, or maintaining your machine itself. So if you start seeing any consecutive results of these actions, you have to investigate. Changes in microbial flora type and numbers of predominance of specific organisms, even they are not over your limits. You have to maintain the knowledge of this information and keep them on your trending. Again, the same definitions are here. What you're going to do if your action limits are exceeded, or how you're going to handle it as a deviation. It's still on our environmental monitoring part. One important thing for the monitoring systems and for classification, we start seeing two different tables. And these tables, as you can see here, qualified state, for grade A, B, C, D, we have the limits of our non-viable monitoring system. Classification, we are relying on the ISO 14644-1.1, or if you want, you can add 1 micron. But for monitoring, 2020 draft still keeps these 5 micron particles because we all know that this is a quite important parameter for our production line. Again, the same descriptions for grade A zones has to be monitored, and also suitable flow rate, at least 28 liters, if the production itself is suitable for this. And the system should frequently correlate each individual sample results with the limits in table 6 at such a frequency that any potential exertions can be identified and responded to in a timely manner. And again, it's recommended that the same system will be installed in grade B. Even you are your frequency may be decreased. An important thing is function of the sampling rate of your system to be used, and still the same definition is here. It's not necessary for the sample volume to be same as the used for the formal classification, which is 1 cubic meter of air for the monitoring system. Your monitoring flow rate will be justified and limits will be defined based on your per minute sampling. Again, 5 micron could be an unnecessary false counts due to electronic noise, stray light, or coincidence, which we described in 2008 version already. And the consecutive or regular counting of low levels may be indicative of possible contamination events and should be investigated. This could be an HVAC system failure, poor practice during machine setup, or even an engineering study requirement. For non-viable particles, it's still the same, the initial qualification process and ongoing routine monitoring and the periodic review of your data. There are 3 different sections. And I'm going to give you one example regarding the cleanroom particle monitoring system design and the risk assessment. In most of the cases, we are seeing cleanrooms and our production line in pharmaceutical industries like this. And our idea, our main goal is to keep everything within the limits where we are showing everything in a green. However, in some cases, in some location, we might have a high count where we are exceeding our limits. This is safe. This is not a big deal. However, you have to know the main reason. If you know the root cause from the studies where you did, for example, on your media field, then you will be on the safe side. If you know the result, if you know the reason, and its consecutive results, then you'll be safe. For example, for particle counters, if you start having a high count, you don't have to worry and never stop your production line. That's the worst decision you can ever make. Reason, maybe the one-time failure happened and will never happen again, and you know the root cause of this problem. Only one peak, one small peak. Even GMP has allowance for these small peaks. But if you stop your line, you will keep your production in danger. You will keep your vials, ampules underneath these conditions, and most probably you will have more consecutive problems on your production line when you go back to production again. That's why know the reason, take the action, and make sure that your microbiological sample data protects you and backing you with the limits. If you take a look at these production line, for example, we'll be simulating an example from this as a risk assessment and the monitoring plan. In order to select right location, every 30 centimeter, you might need to place one particle counter. This will be a 100% coverage of all your risk. In reality, it is not. If you start using this much of a particle counter in every single location, most probably the auditor will make a major comment on your system and will say to you that you are interfering in your production and you don't know your real risk. That's why you increase the number of sample location. That's not because you want to be on the safe side. This is because you don't know what you are dealing with. That's why let's understand what's our risk first. We have our operators on the right side of our production line. And after the pyronization tunnel, our product goes into the system to the accumulation table, and the table turns counterclockwise so that collects all the vials into our system. And we send them directly into the filling line to the needles. And after stoppering or semi-stoppering, we are sending them to the exit of our filling line. So if you take a look at this, our risk points during this process will be these locations. So this first one will be covering our turntable on the accumulation side. The second one will be covering our the needles on the left side most probably. And this Third one will be covering the other half of our needles while the needle system is moving, and also stoppering. And the final location will be taking care of our star wheel and the ejection of our filling line. So these 4 locations will be able to monitor all the requirement while we are moving forward. So for the risk assessment, we have to make the probability versus severity conditions. For example, if you are talking about the viable or non-viable contamination risk, the probability is always high, because if there is any particles that are in our system, the impact, the severity will be always high. If we don't have the conditions where we are not expecting this, the probability will be high too. So there is class number 1, 2, and 3. These classes are not the same classes where we are using for cleanroom classification for sure. This is just a class of our severity versus probability. So we are converting them into our risk classes. So risk class number 1, 2, and 3. If you consider particle systems, your severity will always high and the probability is always high because we are maintaining the system underneath these conditions. So if you are able to detect with a high detectability, then the priority will be number 2 because your risk class will be number 1 and the probability will be, detectability will be high. So the probability will fall into probability number 2. But if you are not able to detect, on the other words, if you're not monitoring your filling line, then your detectability will be low and your priority will be number 1. Let's take a look at our risk assessment file for the turntable example. If I have a vial filling room with a turntable before the filling inlet, my likelihood for particles is high and the impact will be high. So both severity and probability will be high. So my class will be high as a class number 1, the red zone. And detectability is low because I don't have a monitoring system yet. This is my pre-risk assessment. That's why my measure, the location requires non-viable monitoring sensor based on our risk assessment. So when I place this monitoring location into my system, I cannot change my likelihood and impact if there is a particle. However, I will be able to detect it. So my priority will be medium, number 2, because I'm able to detect if there is a particle so that I can warn my operators. So the post-risk assessment allowed me to put my risk into the medium level. The priority of my location become a medium from the priority number 1, the high. So that's the presentation for today, and the following will be the next month from ISCC member, VCCN, the Dutch Contamination Control Institute. We'll be sharing the details along with our colleagues, but I want to introduce you our International Symposium on Contamination Control, which will be held in Antalya this year, 11th to 13th of October. We have a very short video what I would like to show you.
The International Symposium on Contamination Control will be held on 11th to 13th October 2022 in Antalya. The theme of this year's symposium is Contamination Control Everywhere in Our Lives. Life is a journey. Everybody has mornings to wake up to, lands to fly on, horizons to look at and dream about, moments to capture, ages to take. Even though it goes unnoticed, contamination control is sitting at the very heart of our lives, from the very beginning up until the very end. The delicacy of health industry creates the need for isolating rooms, cleaner operation theaters, and intensive care units. Every step in food industry must be checked by means of contamination. Pharmaceutical sector has gone so far with the use of biotechnology. Employees working at hazardous production lines and products with sensitive substances are protected thanks to contamination control. Contamination control and clean room technologies play a crucial role in our lives. With the newest technology in health, food, electronic, aerospace, and pharmaceutical industries, things have advanced a lot. Companies must adapt their productions to opt for a sustainable environment. We are responsible for providing a livable earth for future generations. Cleanroom Technology Society of Turkey was founded with the purpose of meeting the educational demands of people working in fields related to clean rooms and contamination control, cooperating with international institutions about the standards of the sector and making news and developments of the industry accessible to everyone. The 25th edition of the ISCC Contamination Control Symposium will be held in Antalya by Cleanroom Technology Society of Turkey. To participate in the symposium while getting closely acquainted with the Turkish culture and hospitality. Enjoy the beautiful city of Antalya. We welcome all the contamination professionals and experts to share their knowledge and meet colleagues on 11th to 13th October of 2022 in Antalya.
So we'll be more than happy to have you on our contamination control symposium. Our website is live. You can also have your articles and your abstracts because we are still getting abstracts from worldwide, and we'll be planning to have our agenda soon. But you can get more details on www.ISCC'22.com, our official website. I'll be checking for the question session to see. Okay, there was a small shortage on the live stream. We're so sorry about it. Actually, we will have the recorded event on our website, ISCC'22 after this event. So we'll be sharing the link. So if you're not able to follow the full webinar, feel free to visit it again, and it will be fine. Okay. So I'm not seeing any other questions on the chat box. So hope to see you in Antalya this year, and have a great day. See you on our next webinar next month. Thank you.